There are two objectives in this section. First, use exponential function to model compound interest. Second, define the slope of exponential function. Look at the definition. An amount of P dollars is deposited in an account at an annual interest rate R in decimal form. Interest rate R must be in decimal form. And the P is total amount deposit in account. What is the balance in the account at the end of 1 year? The answer depends on the number of times, and the interest is compounded according to the formula. N represents number of times. So look at this formula. A is a balance, P is a deposit, and the R is annual interest, N is number of times. For example, the result for a deposit of $1,000 at 8% interest compounded N times a year. So we have $1,000 and the annual interest is 8% and compounded N times a year. If the interest is compounded for 1 time a year, so the total balance at the end of the year is $1,080. And if the interest is compounded for 2 times a year, and at the end of a year, the total balance will be $1,081.60. And if the interest compounded 4 times, meaning that quarterly a year, so the total balance after a year will be $1,082.43, and so on. As n increases, the balance A approaches limit. To develop this limit, look at the following theorem. Limits 1 plus 1 over x to the power of x when x tends to infinity, where the expression here can be written as x plus 1 over x. They are equivalent. And when x tends to infinity, the value is about 2.7. Look at the proof. This is the expression. And when the x tends to infinity, look at this table. When the x equal to 10, the output is 2.59374. And when x tends to 100, the value is 2.70481. And look at 10,000. When x tends to 10,000, the output is 2.71815. And look at 100,000, the value 2.71827. And look at the 1 million, 2.71828. And the value here actually is exponent. You can try the value. Since the x tends to infinity, you can try 100 million and so on. So what is the value? And so on. The value will be converged to 2.7. That is exponent. Take another look at the formula for the balance A in an account in which the interest is compounded n times per year by taking the limit as n approaches infinity, meaning that when the interest is compounded for infinite times. So based on the formula, we put the limit n tends to infinity, and after that we rewrite our formula where the r over n can be written as 1 over n divided by r, and the power n can be written as n over r times r, and we let x equal to n over r. And you know that the x is proportional to n. So when n tends to infinity, the x also tends to infinity. So the x tends to infinity. And since we have let x equal to n over r, so here can be replaced by x, and here as well. And for this expression, we have proven when limit 1 plus 1 over x to the power of x when x tends to infinity. The value of this expression is about the value of exponent. So can be written as exponent. So this is a formula for the interest is compounded for infinite times. Look at the example. This limit produces the balance after 1 year of continuous compounding. Look at this, the bold letter, continuous compounding, meaning that it's infinite times. So for a deposit of 1,000 at 8% interest compounded continuously, the balance at the end of 1 year would be, we use this formula, P, E, and R. Remember, R must be in decimal number. And this is the answer. So far, we have two formulas. Look at the definition. Let P equal to amount of deposit. T, number of years. A, balance after T years. R, annual interest rate in decimal form. N, number of compoundings per year. So we use the formula according to our situation. We use the first formula when we know the interest is compounded for n times. How many times is specified in the question. And for the second formula, the interest is compounded continuously. We have an example at the next page. Look at this example. A deposit of $2,500 is made in an account that pays an annual interest rate 5%. Find the balance in the account at the end of 5 years if the interest is compounded quarterly. For A and B, monthly, and C, continuously. For the A, so we based on the first formula, because we know how many times the interest should be compounded in a year. Quarterly, meaning that 4 times a year. So P is given 2005 and the R is given annual interest rate 5%. So convert in decimal form 0.05 and N over N. N is because quarterly, so 4 times a year. N is 4 and the T, how many years? 5 years. And you just calculate, you will get the answer. And for monthly, you should know a year we have 12 months. Look at the B. So the N we change to 12 and you calculate. The C, because it is compounded continuously, so we use the second formula. P is given, R is the annual interest rate 0.05 and year 5. And this is the answer. Look at the second objective. Of all possible bases, our base can be 2, 3, 4, 5, and so on. For an exponential function, there is one that is most convenient for the purpose of calculus. The choice of a base b is influenced by the way the graph of y equal to the b power to the x crosses the y-axis. Figure below shows the tangent line to the graph of y equal to 2 power to the x and y equal to 3 power to the x at the point 0, 1. So you can look at the base. For the first function, the base is 2, and the base for the second function is 3. And you observe the slope. The slope is actually increased. Look at these two graphs. I have drawn for you the two functions. For the function 2 power to the x, you can look at the tangent line. I drew the tangent line as well at the point 0, 1. And I read 2 points on this tangent line. So the first point I select 1.5 and 2. And the second point, I select this point. It's negative 1.25 and 0. Where this point is easier for me to read from the x and y. And then I use the slope formula to calculate the slope of this tangent line. I found that the slope is about 0.73. Where for the second graph, the function is 3 power to the x. And I perform the same method. And I try to get the 2 points on this tangent line. And I use the slope formula. I found that the slope is about 1.0556. It's about 1.1. So, meaning that you can conclude when the base increases, the slope also increases. It turns out that some of the formulas of calculus will be greatly simplified if choose the base b, so that the slope of the tangent line to y to the equal to the b power to the x at 0, 1 is exactly 1. In fact, there is such a number and it is denoted by the letter exponent. So we have proven when we have a function 2, power to the x. The slope, this is a function, and we have a slope, it's about 0.7, and we have second function is 3 to the power of x. The slope is 1.1. We round up, so we have about 1.1. And how about the base is exponent? The exponent value is between the 2 and 3, it's 2.7. So sure, the slope of this function is between the 0.7 and 1.1, and we conclude by 1.